Today we are going to talk about chapter 7, the central limit theorem. So in this chapter, you learn about the sampling distribution of the sample mean. You study how it behaves, and you understand how we can apply the central limit theorem, the most important theorem in the history of statistics. Okay, so let's hop on. First, let's look at some terminologies, okay? So we have a new terminology, sampling distribution of a statistic, okay? So what is sampling distribution of statistic? It is the probability distribution for all possible values of a statistic computed from a sample of size n, okay? So if you recall in chapter 1, what is statistic? Statistics is a value is extracted from the sample data, okay? Sample data. So for example, like from your sample data, you may consider the mean of your sample data as the variance. So they are statistics, okay? So for our class, we focus on studying the sampling distribution of mean, okay, of mean. So let's look at an example so we can understand better about this concept, okay? So for example, like we want to study the mean weight of a US infant, okay? So in this class, for example, I give you a project. Each of you will go ahead and collect your own data, okay? And by randomly chosen 100 infant, okay? And you start measure their weight, okay? And from that, each of you, you can come up with different value of sample mean, right? So maybe for one student, his mean from the sample, the mean weight of the infant baby from his sample may be 7 pounds. Another student may get the mean is maybe 6.5 pounds. Another student may get a mean of weight maybe 7.6 pounds, okay? So basically, like all these means, even though we may not know what exactly the value, but with sampling distribution, okay, we can know how they behave, okay, how they distribute it, okay. So in the second slide, we talk about central limit theorem. It's the most important result of statistics, okay. It's a specify how the sample mean distributed, okay. So let's look at central limit theorem here, okay. So it say what it say here. For n observations from x1 to xn, randomly draw from population with mean mu and standard deviation sigma, okay. So if the requirement star in the next slide, okay, when we talk in the next slide about the requirement star, is satisfied, then the average values, okay, x bar equal to x1 plus x2 plus xn divided by n, if you approach just a normal distribution with mean mu and standard deviation sigma divided by square root of n, okay. So this is how we write it. X bar go to normal with mean mu and standard deviation sigma divided by square root of n, okay. So the beauty of this theorem is that even though we don't know what is the original distribution, okay, of the data, but if we know it has a mean mu and standard deviation is sigma, okay, then your x bar, the sample mean, it always converge to a normal distribution, okay, with mean mu. And now standard deviation will be shrink a little bit to sigma divided by square root of n. Here, n is your sample size, okay? So maybe look at the first slide at beginning here, okay? So here you can see, for example, like this how, you know, the infant weight, right? Distributed, the true nature, okay, which we don't know, right? But I say it has some mean mu and it has the standard deviation is sigma, okay? So if you take a sample of size n, okay, even though we don't know exactly the value, I don't know exactly what the sample mean value of your data is, but I know all of your the data collected by all students in this class, okay, for each sample mean here, okay, so say for this class we have 37 students. So if we have like 37 here, we will have 37 different x bar from each of your sample, right? But we know that it will distributed by the normal the bell-shaped nature, okay. So it will cluster around the true mean mu of the infant weight, and its has standard deviation is sigma divided by square root of n, okay. So how we can apply the central limit theorem? So basically, it requires some condition need to be satisfied, which is the condition star in this slide, okay. So what is condition star here? Condition star is require, in order to apply the central limit theorem, we have either one of two conditions below satisfied, okay? So either you have a big enough sample size, so roughly speaking, it's n greater than 30, okay? Than 30, okay? So if we have that condition satisfied, we just roughly speaking say we have a large enough sample size. So at the time, central limit theorem always applicable, okay? And in the case we have a smaller sample size, okay? Sample size say n less than 30, maybe we can put equal sign here, okay? Just speaking like that. And then we have a small sample size. And at that time, in order to apply the central limit theorem, we require the original distribution, it must be a normal distribution, okay? So if we have some small sample size and your original distribution is like this fashion and the central limit theorem not applicable, okay? And at the time, if you have small sample size, which is n less than equal 30 here, I put here, and in order to apply it, we require the normal distribution for the original distribution, okay? Yeah. But if you have large enough sample size, so here we just roughly speaking say bigger than 30, and then it doesn't matter how the original distribution, distributed, right? It can be normal, it can be exponential, it can be uniform, okay, whatever, okay? But basically, like, we will always have it, the central limit theorem applicable, which means it tells that the x bar will only follow a bell-shaped distribution, okay? So be very careful when you use central limit theorem. In order to use it, you need to check either these two conditions satisfied, right? And if it's the case you have like both satisfied, it will be the best scenario, right? But at least one of them must be satisfied in order to apply that, okay? So let's look at the example first, okay, tablet user age, okay, so you can understand better how the central limit theorem is applied here, okay. So a study in 2012, okay, reported that the mean age of tablet users is 34 years old, and the standard is 15 years, okay. So this is what the report tells us, right? Describe the sampling distribution of the sample mean of tablet user age for the following, okay. First, random select 33 tablet user, okay. So basically, like what happened in here is that like you go ahead and survey 33 tablet user people, you ask the age, right? And then you calculate the sample mean of what's the mean age of your sample data, right? And here, the question asks you is that like how the sample mean is distributed, right? The sample distributed. So this is the type of question, where you first identify how the central limit theorem apply here, right? So here, remember, we are considering 33 tablet user, right? So let's look at central limit theorem. What is said here? So if you have n observation, here in this case, we have like part A, we have like 33, right? N equals 33, x1, x2 to x33. And randomly draw from population with mean mu and standard sigma, right? In this case, our mean mu is 34 and sigma is 15, right? And then basically like if requirement star, next slide satisfied, right? So requirement star, what is this? If n greater than 30, right? In our case, n bigger than 30 because n is 33 for part A, right? So basically at the time, central limit theorem applicable because we have one condition satisfied, right? So we don't need to check for another condition. So which means we can apply central limit theorem and say that average value, so in this case, x bar, right? Our case for part A will be equal to x1 plus x2 and plus 2x33 and divide by 33, right? Which is the average age of 33 people in your sample, right? If you approach a normal distribution with mean mu, so mean will be mu. In this case, remember, your mean, just original mean, right? Mu is 34. And standard deviation is sigma by square root of n. So you remember here, the sigma here is 15, right? So in this case, our x bar will follow a normal with mean 34 and standard deviation is 15 divided by square root n, which is 15 divided by square root 33, right? So basically, we can write that in this case, we have x bar here, will follow a normal with mean 34 and sigma 15 divided by 33 square root, right? So this is how you solve the first part, okay? In the second part here, like we consider a bigger sample, right? Where in this case, we have a sample size 100. So what is the distribution of X bar, right? For when we have like the sample size 100. So in this case, again, just go back to the central limit theorem, right? For n observation, here in this case, n equal to 100, from x1, x2 till xn, which is till n 100. Randomly draw from a population mean mu, which mean is 34 for this case, right? And standard deviation is sigma, right? Sigma in this case, which is 15. If requirements star in next slide satisfied, right? So star, which is in this case our n is 100, so it's even better than part A, right? It's bigger than 30. So which is the central limit theorem applicable here. Then again, our x bar in this case equal to x1 plus x2 plus still x100 and divided by 100. It approach normal distribution with mean mu and standard sigma divided by square root n. So in this case, we can write that our x bar will be follow a normal mean 34 and standard deviation is 15 square root 100, right? So this is how we answer part B, okay? You can also calculate by decimal place by using TI, right? What is 15 divided by square root 100, which is about 1.5, right? 1.5. And here in part C, you random select one tablet user, right? So in this case, your sample size only one. And in this case, you can see that actually, because it's just one sample size is one. So basically, it's just the mean now. It's just x1 divided by 1, which is exactly x1, right? So it's just the original distribution of the tablet user, right? But here we don't have anything. So basically, like we have no information about what's the original tablet user age, distribution of tablet user age, right? But here in this case, because we don't have the original distribution in the tablet user age, so basically we just know that it has the same distribution as the original one, okay? Original one. But say if you want to look at the central limit theorem, you can see that basically like the requirements start here. So the first condition not satisfied, right? Because n is 1, which is less than 30. And here it requires, if we have a less than 30 and we need original distribution, normally distributed. But this case, you can see, it didn't say anything about the original distribution. So basically, like the central limit theorem, not applicable here. But we also can have some additional information because we only have one tablet user. So basically, like for this case, the sample mean is just exactly the same as the original distribution. Okay, its distribution must be the same as the original one. Okay, so how about part D? Okay, random select 10 tablet users, right? So again, we just go back and see if we can apply the central limit theorem and say anything about the distribution of the mean age of 10 people, right? 10 people for example, 10 people. And here like n equal to 10 observation, x1 to xn, randomly draw from population with mean mu. In this case again, mean mu is equal to 34, right? And standard deviation is 15. If requirement star, next slide satisfy, and again we check it, right? So in this case, n equal 10, which is not satisfy the first requirement, right? And n less than 30, right? Which is in our case here, property. But again, we don't have any information about the original distribution. So basically, we cannot apply the central limit theorem. So basically, for part D, central limit theorem not applicable. You have no clue about what is the distribution X bar. We don't know. For this case, we may know that it has the same distribution x1 as the original distribution, right? Original distribution. So if the original one is a uniform, is a uniform. If the exponential is exponential, and we do have other kind of distribution. But the scope in this class. Okay, we only consider uniform and normal. If some of you who are more advanced, you can look at the textbook and learn a little bit more about the exponential case. So let's look at example 7.3, so we can see how we can apply central limit theorem to calculate the probability. Okay, so this problem about credit rating. Okay, so bank's loan officer raise applicants for credit. Okay, right, and score normally distributed between 200 and standard deviation 50, right? 50. So it tells us score normally distributed between 200 standard deviation 50. Okay, so randomly choose one applicant, find probably his score between 180 to 198. Okay, so this first thing first. Okay, let's look at part A. Randomly choose one applicant. Okay, so let's formulate this problem. Okay, so if we know X at the rating score, right? And the problem, it tells us X rating score normally distributed. So it we mean 200 and 150, right? So we can write X follow normal 250, right? 200 is the mean and 50 is standard deviation, right? And in part A, because we randomly choose one person, right? So as we just see in previous example, so the mean here just exactly x1, right? And if you want to look at from a central limit theorem perspective, and then basically we check the requirement star in next slide, right? In this case, we can see it's satisfied, right? The first condition violated because any one. But the second condition is that like we have original distribution is normally distributed, right? Because it gives us here, right? Score are normally distributed. So we can apply that, but more or less you can see even you apply central limit theorem here, your n is 1, so your x bar just follow exactly normal with mean mu and standard is sigma by square root 1, which is sigma, mu sigma. So just the same as the original distribution, the same as original distribution. So from that, we can specify the distribution of one randomly selected person, right? And we find the property hit score between 180 and 198. So just find x1 from 180 to 198. And we already know that x1 follow normal 200 and mean 50, right? So it's come back to the problem of chapter 6, right? You have the values you want to find the error under the curve. So which is you just do a normal CDF. Lower bound will be 180, upper bound 198, and mean is 200, and standard deviation 50, right? And if you plug in your TI calculator, you should get 0.139, right? 1.39. Let me just quickly show you how we perform this task from the calculator, right? So you can see it, right? Let's see. TI calculator online here. Let's see. Okay, so you do a second distribution here. And you do normal CDF, which is the first option here. Enter. Oh, sorry. It should be normal CDF, not PDF. Okay. Which is second option here. Enter here. Clear here. Why is normal PDF again? Let's see. Let's see. Second option. Are we clear? Let's see. Normal CDF. Oh, not. Let me see. Delete. Quit. Maybe I will quit it and see. Let's see. How do I quit it? Let's see. How do we quit it? Quit it. Okay. Quit. Okay. Yeah, it's quit here. So say again. Okay. I'm sorry for that. Second distribution. Normal CDF. Okay. Lower bound is 180, I believe. Up about 198. And then 200. And then 50, right? This is what we have. 0.139. Okay, if we keep 3 digit, okay, we keep 3 digit. So try to make sure, okay, you work on this, so this way, when you go to the test room, you're confident about that. See, if you plug in your TI calculator, this is what you get, 0.139 with a normal CDF function, okay? How about prop B? You randomly choose 80 applicants and you want to find the probability the mean score is above 215, right? 215. So in this case, you have a sample of 80 applicants and you calculate the mean score, right? Mean score. So in order to find the probability their mean score is above 215, the first thing you need to do is that you need to specify the distribution of the mean score, right? Which is X bar, right? So in this case, we just come back to a central limit theorem because central limit theorem, it allows us to specify how X bar distributed, right? So again here, for n observations, so in that case, n is 80, okay? X1, X2 to X80, randomly draw from population with mean mu. In this case, our mean mu is 200. And standard sigma, which is our case, and the sigma equal to 15, okay? If requirement star next slide satisfied, okay? So next slide, which is in this case, n greater than 30, right? We have n 80, 80 greater than 30, so which means it's obviously satisfied, right? So very good. So we can apply this, right? The central limit theorem. X bar will follow normal with mean mu. So we mean mu, which is 200, but standard will be shrink to sigma, which is 50, divided by square of n, which is divided by square of 80, right? So in this case, you can see that X bar will follow normal 200 and standard 50 by square of 80. So which means if you do some calculation, you get like normal 200 and 5.59, okay? And because it asks us to find the probability the mean score is above 215, right? So which is, in this case, probability X bar greater than 250, 215. So we just do a normal CDF. So in this case, the lower bound will be 215. And the upper bound, we just put a big number, right? So in this case, just put 9999. For sure, you can replace this upper bound by any value bigger than mu plus 4 sigma, which is 4 times mu 200 plus 4 times 5.59, right? But I'm lazy, so I put 9999, which it will work most of the time, right? And then the mean 200 and standard 50. And if you do that, you get 0.04, okay? So just perform second variance and then normal CDF, give the lower bound, upper bound, mean and standard deviation, right? Oh, I'm sorry, it should be 559, right? 559. Let me see. Okay. Okay. It should be 559. Yeah. And then in part C, what it asks here, randomly choose 80 applicants. So pretty much the same as part B, right? In what range you should expect to find the middle 36% of most average credit score, right? So in this case, basically it's just a type of inverse norm problem, but it's a bit more specific. So basically, like, let me just quickly give you this slide, okay? In the another slide here, so you can see new slide here, okay? So basically, your X bar from part B, right? We know that X bar will follow normal with mean 200 and standard deviation is 559, right? X bar follow normal 200 and standard deviation 559, right? And so probability of X bar, what asking, what range we would expect to find the middle 36% of most average credit score, right? So basically, we want to find, I think it's here. Okay, that's fine. That's fine. You have your normal. This means 200. And standard deviation is 559, right? And then you want to find the range A and B, okay, where we have the most 36% of the data, right? I draw a little bit bigger than 36%, but yeah, this is just a basic idea, right? You can understand here. So basically, like it asks you to find A and B symmetric around the mean, right? Which property A less than x bar less than B equal to 0.36, right? 0.36. So basically this just the question C, right? Question C. So again, if you have a very fancy calculator, TI 84 plus CE and above, you just plug in invert norm and you give the error 0.36 and you tell calculator you're working with center and it should give you the answer very quickly for A and B, both of them. I'll show you in a second, okay? But say if you just have a TI 84 older version and TI 83, and then we need some additional labor, right? By specify what is probably X bar less than A, what probably X bar bigger than B, right? And then from that, we will find A and B one at a time, right? So in this case, you can see the error in the middle, which is the dash here, is 0.36. And the total error under the curve is 1, right? So basically we have that x bar less than A, which is this first part here. And this is the second part dot here, x bar greater than B, right? Plus x bar from A and B plus x bar greater than B equal to 1. The total error under the curve is 1, okay, always 1. So which means, because the middle is 0.36, so which means x bar less than A plus x bar greater than B equal to 1 subtract 0.36, which is 0.64, right? And because symmetric, so basically x bar less than A, this first dotted sign here, equal to the second dotted sign, okay? So we have like x bar less than A will be equal to x bar bigger than B and will be equal to 0.64 divided by 2 or 0.32, okay? And from that, because x bar less than A 0.32, which it come back to the problem of finding the 32 percentile value, right, of x bar, right? So basically you should do invert norm 0.32, 200, and 559, and you get 197.386. And you can see here, your probability x bar less than A equal to 0.32. So it's just, A basically it's just the 32 percentile value, right, of x bar, right? So you can do inverse norm of 0.32, the mean is 200, and standard is 559, and if you plug in your TI calculator, you get a 197.386. And for B, if you have fancy calculator, it will be fast, right? But if you don't have that, you have a TI-84 older, maybe old version, or maybe TI-83. So basically, like you need to do some labor by translate the right, which is x bar greater than B, to the left, which means you find x bar less than B, which is the complement of x bar greater than B, right? So it be probably x bar less than B be 0.68, right? And then again, with the left side, which is all the calculator TI from 83, it can perform. Basically, yeah, B will be inverse norm of 0.68, 200, 559, and you get a 202.614, okay? So let me just quickly show you how to perform the inverse norm function, okay, from the TI calculator. So in this case, you can do, okay, here. So the first one for A, right, you do second, and variance here, you go to invert norm, the third function here, right? You give the area will be 0.32. The mean is 200. The standard is on 559. And remember, we're talking about left tail, right? Left tail. So which work for all the TI, right? All TI work for left tail. But this is a fancy calculator. It's a TI-84 plus CE. So it has center and right. So if you have this type of calculator, your life will be much easier when you deal with this type of problem. Okay, you don't need to do additional labor. I'll show you very soon how you just don't need to do transformation like I just show you and still be able to get A and B. Okay, but here I am working with the version where you have the older version calculator. So you get like 197.386, right? If you keep 3. And the same thing for B, it's just the inverse norm of the error is 0.68, right? Everything is the same, paste here. 202.614, right? And say, if you do have this type calculator, right, in the test, and they ask you this question, right, and you just do here, you give just a 0.36, which is the middle, right, most here, and you tell the calculator, this is the area of the center, right? You see here. So see, the low bound, 197.386, which is exactly the same what we do here for A, and 202.614 exactly we got for B. So your life a little bit more comfortable, you say sometime you have this calculator. But I think, even you have a older version, it's not that bad calculation, right? Just 1 or 2 step more. So let us look at another example 7.4, AirPods Pro listening time. Okay, so here Apple they claim that their battery listening time of a full charge Apple product, AirPods Pro, normally distributed between 5 hours and sometimes 0.6 hours. Okay, and here you feel doubt about this claim and you just want randomly select 9 AirPods Pro and check the claim, right? So the first question here, what they ask, can the central limit theorem applicable for our sample mean? Okay, so here we consider about the mean listening time of 9 AirPods Pro. Okay, we used to check the claim. So see whether it's applicable or not. So basically, we need to check if the condition star satisfied. Okay, so to look at this problem again. Okay, so here the original distribution is normally distributed, right? With mean 5 hours and standard 0.6 hours. So which means the original distribution is a normal with mean 5 and standard 0.6, right? So when you check the central limit theorem, which is you check the requirement star here, right? We have sample size big enough or not. In this case, N9, which is the first condition not satisfied, right? And in the case N less than 30, right? Which is 9 less than 30, we need the original distribution. It must normally distributed. And then here, it already normally distributed. So it's satisfied, it's applicable here, right? And then because it's applicable, so we can process further tasks, right? So B, find probability mean of sample from 4.9 to 5.6 hours. 5.6 hours. So let's do it. So, but first and first, you need to specify what's the distribution of the sample mean, right? What distribution X bar. So here we make this problem a little bit more formal. If we do know X variable represent the AirPods Pro listening time, right? Then X will follow normal 5.06, 0.6, right? 0.6, as stated in the problem. And then if we know X bar is average listening time of 9 AirPods, right? And then we can apply the central limit theorem. So the central limit theorem tells us, okay, X bar follow normal mean mu. So in this case, mu will be 5, right? And standard division is sigma by square root of n. So in this case, will be 0.6 divided by square root of 9 because we have 9 AirPods, right, in our sample. So in this case, we can find X bar will follow normal with mean 5 and standard 0.6 by square root of 9. And we can make it more specific by just do this calculation, right? And you got like normal 5.2, right? And the question is that find the property of the sample mean, right? Between 4.9 to 9.6, 5.6 hours, right? Such that find this probability, X bar from 4.9 to 5.6, right? and it's just a normal CDF problem, right? Yeah. Normal CDF, low about 4.9, up about 5.6, mean is 6, mean is 5, and standard 7.2. And if you plug in your TR calculator, this is what you get, right? 0.681, right? So probability of the mean listening time of a sample size 9 is from 4.9 to which is from belong to 4.9 to 5.6 is 0.681. Okay, and you can say another way, like, you know, if you collect 9 randomly sample, 9 randomly AirPod Pro. You can say, you can also say that if you just randomly collect 9 but AirPod Pro, and you calculate the mean listening time, and among like 100, you know, people who collect data independently, right? And then like about 68 of them, right? We have the mean listening time in the sample will belong to 4.9 to 5.6. So there are different ways we can interpret this result, okay? And what is she asking? She asking for the 80 percentile for mean listening time of the sample, right? And interpretation this result. So this is just the 80 percentile problem, right? 80 percentile problem. So what you can do is that it's just an invert norm type problem. The 80 percentile problem, right? So basically, you want to find the value or where you know 80% of mean listening time less than that value, and 20% bigger than this value, right? So basically, you just do invert norm of 5.2, which in 0.8. I think that the order would be reversed, right? Reversed. So this much, right? So you do invert norm here, and you should be able to get the value here, right? And interpretation here, just 80% of average airborne listening time from a sample of size 9 is less than 5.186. So interpret value, the 80 percentile value, just inverse norm of 0.8, 5, and then 0.2, and you get like 5.168, right? The interpretation here would be 80% of the average airborne listening time from a sample of size 9 is less than 5.168, right? 1.68. So now we look at the quiz 7.1. Pregnancy lengths are normally distributed with mean 268 and standard 15, right? 15 days. So we have a pregnancy length is follow normal mean 268 and standard 15 days, okay? In part A, if one woman is randomly selected, find her that probably that her pregnancy lasts less than 260 days, okay? So let us, make the problem in the kind of formula shape. So if you know X is the pregnancy length, right? Random variable length. Then the problem tells us X will follow a normal with mean 268 days and standard deviation 15 days, right? Our mean here and standard deviation here, okay? In part A, if one woman is randomly selected, okay? So this problem, it come back to the first example, the second example, right? 7.2 and part C, right? And basically, what we have is that it's just the original distribution, right? So which means part A, right? If you have one woman reselect and her pregnancy length is just the original one, same as 268, 15, right? And find the probability her pregnancy lasts less than 260. So this is just probability x1 less than 260, right? And which is a normal CDF type problem, right? You have the value, you want to find error under the curve. So maybe put something small here. Anything less than the mu subtract for sigma, right? but I just put here because I'm lazy, right? I put 260, the upper bound, 268, which is the mean, and start as 15, right? So if you plug in your calculator, you should get the property of a randomly chosen woman, their pregnancy length less than 260. Okay, 260. So let's do this together. Okay. Part A. Second, events, no more CDF. Low bell, no, they put something small already. We don't need to take care of that, right? 260, we need 268. Yes, that's 15. So 0.297, okay, if you keep 3 digit, 0.297, 0.297, 0.297. What we say? If now you have a sample of 10 women, okay, randomly selected, probability the mean length of pregnancy less than 268. So in this case, you have 10 women, right? And each of them will have a pregnancy length, and you just calculate average. So again, it just comes back to the central limit theorem problem, right? So we need to be able to specify distribution X bar, right? So here, for n observations, in this case, we have n equal to 10, right? 10 observations, x1 to x10. Randomly draw from population with mean mu. In our case, mean mu is 268. And standard sigma, in our case, sigma is 615, right? If requirement start in next slide satisfy, so either n bigger than 30, in our case, it's not because we only have 10. And if n less than 30, we need the original has normally distributed. So this thing you can see it already satisfied, right? Because it say that, what is say here? Pregnancy length normally distributed. So second condition satisfied. So which means you can safely apply the central limit theorem. It tells that X bar will follow normal mean mu. So in this case, it will be 268. And standard sigma is divided by square root n. In this case, just 15 divided by square root 10, right? 15 divided by square root 10. So you can specify your X bar, okay? It follow a normal with mean 268 and standard deviation 15 divided by square root of 10, okay? And again, the same thing, right? They ask this value, what property of this value less than 260, right? So you do a normal CDF, the same thing, very small number, 260, mean 268, but standard deviation now change. So originally, you see in A, it will be 15, but now it's 15 divided by square root of n, okay? So let's see if you do that in the TI, what we have here. The TI calculator. Okay, second here, distribution. No more CDF. Very small number. We can put 999. It won't affect, okay? Negative 999 here. 260. 268. And 15 divided by square root of 10, right? 10. It closes. Yeah. So 0.4046, right? 0.046. 0.046. Or to 0.046, okay. And sure, you just can just retain, right? Keep the value, the low bound they just the calculator gave us at originally, right? It won't affect. Let me show you quickly. If you just keep the low bound as the calculator gave us, what happened in here? Okay, just here, instead of using negative 999, right? This is much smaller number. Negative 1 0 0 0 0. You have 99 number 0, right? And then upper with 260. 268, 15 divided by square root of 10. Closest. The same, right? 0.046, right? 0.046. So this is how you solve this problem, okay? 0.046. And see, why can we apply central limit theorem in part B? So why we working on B, we already told that, right? Because the first condition not satisfied, but in this case, the second condition satisfied because our data is follow normal distributed. Okay. Thank you so much for your attention, and I'll see you in next class.